What's up guys and welcome to our third Vedic mathematics video. And technically this is the second because we are now discussing our second sutra, which is the Nikhilam Navatascaramam Dastah. And this literally means all from 9 and last from 10. And I got this straight from our original Vedic mathematics book written by Swamiji. Okay, so now let's discuss when should we use this sutra. So the sutra can help you multiply any set of numbers extremely easily. And I have some examples. It can be 4-digit, 3-digit, 2-digit, you name it. And it is much simpler than what we currently do. So yeah, now here's the thing. This sutra is extremely large. There are a lot of things to discuss. So I split it up into 4 parts. This is the first video, so we're going to be discussing numbers that are close to the base. In the second video, we're going to be discussing numbers above the base. And the third video, we're going to be discussing mixed numbers. Well, mixed of the first two. In the fourth, we're going to be discussing numbers in between the base. And yes, every video we're going to add on to our Python calculator or function, which we will be building every video. So yeah, welcome to our first video, numbers close to base. Alright, so now let's discuss the execution. So here we have 99 times 93. And our base is, well, I should have talked about this before, but here's the base, what it actually means. So the base is the closest multiple of 10, and in this case, it's 100. It's like if you round a number to the closest multiple of 10, that's what it kind of means, and that's going to be 100. And then here we have a couple of terms, which I'll explain them as we go on, but just keep them in mind right now. So the right one is the base minus the left one. So up there, 99 and 93 are left 1 and left 2 respectively. And our base is our base. So right 1 is 100 minus 99, and that is going to be equal to 1. And then we do the same thing for 93. So right 2 is going to be equal to 100 minus 93, which is 7. So now, let's set up our chart. We have our left and right columns, and then we have 99 and 93, and 1 and 7. And the symbol in between looks like a minus symbol, but it really just tells you that when you subtract 99 from the base, you get 1. 93 from the base, you get 7. So, yeah, that's all it means. And then we can set up our lines, and our final answer will actually be divided into 2 parts. And all you have to do is just join them together, literally just join them, and then you get our answer. Alright, so we have to first solve the right portion. To do that, we multiply 1 by 7. So we all just know that's 7. Nothing tricky, nothing complicated. But when you look at the base, you see that there are 2 zeros on the base. And there's a lot of 0 and the length of the base involved in the sutra. But you see there are 2 zeros. So that means the right portion has to be a 2-digit number. Well, 7 is 7. So how do you make that 2 digits? You just add a 0 in front of it. That's it. Alright, cool. Now let's solve the left portion. Now, to solve this, you have 4 options. 1, you could do 99 plus 93 minus 100, or you could do 100 minus 1 minus 7, or you could do 99 minus 7, or its converse, which is 93 minus 1. And if you notice, all of these are equal to 92. Well, when we are programming, we're going to be using our third option, which is 99 minus 7, cross-subtracting. Great, so now we can just put 92, simple, easy, and if that number exceeds, you just keep it. You don't do anything with that number like we did with our right portion. And there you go, our final answer is 9,207. Awesome. Now, let's discuss another possibility that can happen while you're solving this. Here we have 901 times 902. So we want to do this normally, right? So we set up our base, which is 1,000, and then we set up our chart. So we have our left and our right, 99 and 98. But wait, well, how do you multiply 99 times 98? Remember, the objective is not to use a calculator. Well, you just set it up in another chart, and you just make 99 and 98 the multiplicants, and you get 1 and 2. You can multiply 1 by 2, and you get 0, 2. Remember that 0. And then 99 minus 2, or 98 minus 1, you get 97. there you go. You just put 9702 and then 99 times 98 column. Great. Well, now let's solve for the left, and I'll talk about something we have to do with the right after this. So for the left, we just solve 803. Nothing complicated, just 901 minus 98, or 902 minus 99. Great. Well, now we have to remove the 9 in the right portion, because our base is 1000. So the max number we can have in there is a 3-digit number because we have 3 zeros. So we remove the 9, but we add it to 803. And so we get 812 and then 702. And you can just add a comma in between, and there you go. You have 812,702 as your answer. Awesome. Well, now let's discuss some limitations. So this sutra, this part of the sutra has limitations, and these limitations will be solved as we go through. So number 1 is both multiplicands must be greater than 90% of the base, which means things like 9,543 times 3,574 or these two sets can't be allowed because they're not greater than 90% of the base. Hey guys, post-editing me here. I would just like to say 7 times 6 is multipliable. I'm not sure if you noticed that, but any numbers below 10 can be multiplied because the 5 times 5 is already covered. So I didn't implement that, did some testing and experimenting and figured that out. So we're going to fix that in the next version, but for now we're going to keep this how it is, and I'll explain it further in the next video. And this will be solved as we keep going. And then both multiplicands have to be the same length, which again we will solve when we keep going. And this is like 90 times 90 has to be like, they have to be the same length. You can't have like 95 times 9. That can't happen. They have to be the same length, which is 2 digits, or 1 digit, or 3 digit, whatever. And yeah, that's it. So that's all the theory out of the way. Now let's actually go ahead and program everything. Alright, so let's get all of this coded up. I'm going to start off by defining our function. So I'm just going to call it main because I'm not that good at naming, and later we're just probably going to make it the sutra's name, but I mean, that's for later. So actually, I'm going to pass right now because I want to include that Swamiji only requires you to know a 5x5 table, multiplication table, instead of a 12x12 or whatever. So we're going to actually hard code the 5x5 table inside. So right after the function, I'm just gonna, I pasted it. You can take a moment to copy it down. You can pause the video, but I'm gonna explain it. So I'm gonna go over how to use this, but let me just tell you right now. There are zeros on the on both ends. So that is because of the way Python treats the index, right? The index always starts at 0. So for this to work flawlessly, we're just gonna have zeros at the end. So that's it. Just a normal multiplication table. Alright, so now we can get back to this, and the first thing we have to do is define our base. So there are 2 bases actually. There is each number has the base, num1 and num2. But in the low probability, can't even say that, but like in the probability of there being different bases, we want to make sure we capture the biggest one. So for that, we're going to take in both bases, and we'll go over that in a bit. So base 1 is going to be equal to the integer, because we want it to be an integer, of string 1, and then adding on 0. And so we have the 1, and then we're adding 0 multiplied by. So this, the multiplication symbol, is a operation for strings. It's not a multiplication symbol in this context. So it multiplies a string and returns a string. So like if we multiply 0 by 5 as the string 0 by 5, we'll get 5 zeros returned in a string. So this way we can easily, copy out zeros. Now we want to copy them by the length of the string of num1. Because so like how large, so the length of num1 is the amount of zeros our base has. We discussed this. So I have to take the string of the num1 to actually get the length of it. So yeah, we just add a 1 to that. And all we have to do is copy that to create base 2 and num2. All right. And now there is another instance that can pop up that I actually bumped into. This is that if the number is equivalent to the base in a way. Actually, not really. It's like, what if the number is a multiple of 10? So we're multiplying 10 by 10, you could imagine, right? What would our base be according to our program? It would be 100, because the length of 10 is 2. So you multiply 0 by 2 and you add 1. But we don't want that, because as humans, we're just going to calculate 10 by 10. So 10 minus 0 on both. So 10 minus 0, 10 minus 0. 0 times 0 is 0, and then 10 minus 0 is 10. So our final answer will be 100. 10 times 10 is 100, yeah. But as if we let this go, then we're going to get 10 minus 90, multiply 90 by 90, and then get some horrendous mess. And we don't want that. So we're going to make sure that if the number is a multiple of 10, then the number ends up being the base. So we can fix that issue. So how do we do that? We just say if the num1 multiplied by 10 is equal to base 1, then set num1 equal to base 1. Oh no, wait, it's flipped. Base 1 is equal to num1. 1. And now you notice, wait a minute, we're making a multiplication function. We can't use multiplication inside it. Well, you're right. And this, luckily, there's a very easy fix to, which is when we multiply by 10, we just add a 0 as humans, right? The computer multiplies it by 10 by adding the number over and over again. So we can just add a 0, like a human. So, of course, we can't do this. You're right. So let's just do that. So we need an integer of the string of num1. And then we just add a 0. And take that, make an integer, and boom. There you go. So that is now finally valid. And now we can just copy this because we want to do the same for num2. Have base 2, num2. Okay. So now all of that is taken care of. And now, like I was talking about, what if the base 1 is greater than the base 2? Well, that's a problem, so let's just figure that out. So if base 1 is greater than base 2, then we want base 2 to equal base 1. And then else base 1 is going to equal base 2. Now, one variable we're going to add right here is the zeros, because we're going to use the number of zeros in the base a lot. So I'm just going to have a variable for that. So this is very easy to do because we can just take the length of string of base 1 minus 1. It's just the number of zeros, not like zeros physically, just the number of zeros. And yes, we have to do this twice. This one is for base 2. Alright, now all of that is finished. Now we can move on to this thing which I called first priority conditions. These are conditions which will return a valid number without any calculations needed. So, so there are 3 of them. And our first one is if num is equal to 0. So if any number is equal to 0, whether it's num1 or num2, we want to return a 0. Because anything multiplied by 0 is 0. So that's number 1. Number 2 is if either number is equal to 1. If num1 is equal to 1, then return num2, because anything multiplied by 1 is itself. And so if num2 is equal to 1, return num1. And then number 3 is if both, not one or the other, both numbers are less than equal than to 5, because we have our multiple table. If they're less than equal to 5, both of them, we can just pop it out of the multiple table and no calculations needed there. So that's why I have it in the format I have it, so it's easy to pull numbers. Alright, so let's code in if the numbers are equal to 0. So if num1 is equal to 0, or num2 is equal to 0, then we can just return 0. And then if num1 is equal to 1, then we can return num2. Else if num2 is equal to 1, then we can return num1. And then here we have our multiple table condition. If num1 is less than equal to 5 and num2 is less than equal to 5, then we can return multiple table sub num1 sub num2. So because it's an array, we can do that. Alright. I need to add spaces there. Alright, so now we have done all of those. Those are our first priority conditions out of the way. Now we can actually get to the procedures that the Sutra uses. So let's start off. So we know right 1, those are the first things we calculate. So right 1 is equal to base 1 minus num1, because we already calculated our bases and everything. So we know all of that. So after that, let's get our right 2, which is going to be equal to base 2 minus num2. Alright, yes, even though it's all base 1, base 2, even though there's only one base, we'll get to this later. This is our initial version. So we're going to leave it like this. It really doesn't matter. Alright, so now, after we do this, remember how we talked about the numbers have to be greater than 9/10 of the base, or 90% of the base. So if the base is 100, the numbers have to be greater than 90. So this is the point where we have to put that in. And yeah, it doesn't work fully. As in, like, it works functionally wise. Like, functionally, it works. Let me explain. So let's just code it out first. So if num1 is less than equal to... Oh, whoops, I forgot. We actually need a math function here. So just let me... I'll tell you why. So just import math. We need a math function. So we're going to use math.ceiling. So we're going to take the ceiling of base 1 multiplied by 9/10. Because 9/10 is 90%. And yes, we're using multiplication. So we're taking the ceiling of this operation. So that, it's always based off. We're not going to use round. That's too big. Or num2 is less than equal to math.ceil base 2 times 9/10. Yes, I gotta copy paste that. Alright. Yes, we're using multiplication operators. That is not allowed, you're right. But unfortunately, there is not much we can do here. There is literally no way to avoid this. So, again, we only have the knowledge of this sutra and our previous one, and none of them can help us here. So, as we get to learn more sutras, this will automatically be fixed, and we will not have to deal with this. But for now, we're going to need to implement the multiplication operator, even though we're building a multiplication function. So, yeah, forgive me, but that's what we have to do. So, after that, if it is less than, then we can't do it. So we're going to have to return formula not applicable. That's what we're going to return. You know what? I'll make it formal. There. Even the end? Alright. So, I'll do that. That is going to be our return value for if the formula does not work for that particular case. Alright. So, after that, let's continue where we left off. We need to find out our left answer and right answer. So, I'm going to do the left answer first, because why not? So, left ans is just equal to num1 minus right 2. Don't fumble on that. It's num1 minus right 2. It's cross-subtracting. Alright, and then our right answer, And this is the right portion, left portion. So I call it left answer, right answer. You just join them after we do something important, which is carrying. And here, yes, we multiply right 1 by right 2, but we can actually use recursion. Call our function again. Right 1, right 2. This is where it actually works, and you can like actually do this. So yeah, you could just leave that. And now, what if, so we're recursing, of course. We're going through recursion. And you do this, you call a function, and you return formula not applicable. So in that case, we're going to have to do something. I'm just going to copy this, because we're using it twice now. Because if right answer, if right answer is equal to formula not applicable, then we have to return formula not applicable, because we just hit this bar. So we can't do that. Okay, well, that's everything solved, right? Other than the whisper I said, which was carrying. Yeah, we gotta do carrying now. We're so close. We're almost done. Last step. Alright, so now we first have to check if the right answer is greater than equal to base 1. Right? Because we have our base, we discussed how the right answer can't be greater than the base. So we have that, and here we're finally going to use our zeros. So we are going to create a new variable, call it toCarry, and this is where we're taking the front portion of our right answer. We're just taking that and putting it into toCarry. So to do that, we have to take the sub of right answer. To do that, we have to make it a string. So string of right answer, and now we're going to sub. This is so weird. Have a colon, because we're pulling out the very first digit. We're going to say length of string of right answer, and then minus zeros. So it doesn't matter if toCarry is 2 digits, 5 digits, whatever. It can't be 5 digits. It's always going to be 1, I think. So it doesn't matter since we're subtracting zeros. Whatever is left is going to toCarry, and it's going on the other side. So we leave that flexibility. And then what we do is just, we say left answer is plus equal to integer of toCarry. So there you go. So now we just, left answer. So now we just added it directly to the answer as an integer. So, alright. So now we just did all of that. Now we need to fix right answer because it still has the toCarry part. So right answer is going to have to equal, again, the string of right answer because now we're splicing. So we're going to say the length of the string of right answer, and again, minus outside, minus the zeros, and then a colon. Yeah, so colon in the front versus colon in the back. Alright, so now all of that is set up. Now there's only one thing left to do, and that is if our right answer doesn't have a zero in the beginning, and it needs to. Like we discussed, it has to be at least like in length equal to the base's length. So again, we use our zeros, and this is going to be a while loop. It really shouldn't. Like, you shouldn't need to use it more than 5 iterations, whatever. So it shouldn't be that heavy on the function. So I'm just going to say while length of string of right answer is less than the zeros of our base, we need right answer to equal 0, not string. We need to have a 0 plus the string of right answer. So now we're adding a 0 every single time. Ladies and gentlemen, that is where we end. Now all we have to do is return our final answer, which we're going to return as a final integer. So integer of string of left answer, and we're going to add string of right answer, and yes, the integer goes around the whole thing. Like that, yes. So we combine those two, turn it into an integer, and there you go. So many extra lines. We have finished and completed our whole function. Now if you notice, I have this little tab right up here. If we click in it, Wow, that's a lot of stuff. This is test code that I created. So I'm just going to copy this. This is going to help us debug if we need to, and basically test the potential of this function. So I'm just going to paste it right here. So we actually have two parts to this. This is manual number checking. So if we uncomment this, we set our num1 to something, and we set our num2 to something, and it just gives us an answer. Over here, there could be a recursion error since we use recursion, so we want to catch that so we can debug it and get our num1 and num2. And then here we get our answer, and then check, is it correct? Here we use Python's multiplier, so check, does our thing work? So let's put it into 99 and 97, because why not? Let's run that function. Is it correct? True? Yes, it is. 9,603. Great. Now let's give it some wonky numbers. Let's do that. And, well, you get this value error because we're trying to multiply with a string over here. But yes, we do get formula not applicable. That is correct because here we don't have a number that we can use. So you can do a lot more testing with this. I'm going to move on to my next piece of test code. So let's just put this away. This is a exhaustive piece of code. It's an exhaustive search or testing. So here we have a range. And I'm going to graph this for you to tell you more. So we have a count over here. And basically 10, 10. So we're creating 100 equations that this has to solve. And we're going to see how many of those can it actually solve. So if it can solve it, we're going to increase count by 1. And we're going to print out how many out of the 100 it can solve. So here we go. You see, we got a lot of not equal, formula not applicables. So we got 52. Yes. Wait a minute, why did we get formula not applicables here? Alright guys, so while I'm fixing that up, according to YouTube, only 5.5% of you are actually subscribed to my channel. So if you already haven't, go ahead, smash that subscribe button, and it really helps me out a ton. I truly do appreciate it, and if you'd like to see more content, it's a great way to help me out. Alright, back to the video. Okay, whoops, my bad. We actually changed this to be formal, so, okay, now let's give it a try. Clear that terminal. Okay, now we get a solid 52. That was weird. Alright, sorry about that. So we get 52 out of 100, which is about half, which we kind of expect. But what you're going to notice is surprising. So here we just updated 100, 100, which I believe is 10,000. So let's run that. And you see the number drop way less than half. So 446 is how many we solve. We go to 1,000, 1,000. This is 1 million. And it's going to take a while to solve. 4,312. That's very, very less. That's like less than 1%, I believe. So, that's really, really, yeah. So here I have the graph on the screen, and yeah, you can really see that the thing goes down by a lot. So like the number of calculations that we could have solved out of the equations. Yes, this is quite bad, but for the two sutras we know and have figured out, I wouldn't say it's that bad. The fact that we can do so much with this sutra, even though there are so many limitations, it's not bad at all. So, again, we're going to have to fix this problem at some point, but we're going to keep adding on to more sutras, and we want to see that bar go full up. We can solve every single equation. So, yeah, that's it for this video. I will see you in the next one. I hope you learned something new, and yeah, goodbye.